Okay, can you see guys now? Yeah. Yeah, I guess now it is okay. Is that okay? I'm sorry, I don't know what exactly the problem is going on here. Okay. Yeah. So, okay. So okay, yes. Let's continue. So TensorFlow is a very great tool in order to visualize what is the graph we have created till now. And if I am repeating, please don't mind because I don't know where the video actually where the video have stopped. I will be trimming the video after this particular session have been finished. Okay, please don't mind. Okay, so here we pass the input. Yes, here we pass the input, and we the input going to be reshaped, and then it is going to be passed to the convolution ReLU pool 1. And yes, it is again going to be a convolution ReLU pool 2. Two convolution layers again we are having, and then it is going to two affine layers. The final affine layer is what the output predictions are, because it is having 10 classes. Yes. So yes, and finally have defined our cost function as defined here. This is the cost. Okay, here is the cost, and we are adding cost at each iteration as a scalar summary in order to visualize the cost and the accuracy. Even the accuracy have been added. You can see here the accuracy function. Okay, which is fine. Accuracy operation and the cost operations have been added to the scalar summaries, which is fine. And this is our objective function. So it just find out the gradients by itself. The beautiful thing about the TensorFlow and the with the remaining libraries is that the TensorFlow computes the gradients by itself without, with the cost function itself. There is no need for us to define the gradients again. So that is the thing. Okay. So okay. Yes. After passing the input, after training this, I got 99.2% accuracy. So it would take me, if I'm going to run this particular model now, it is going to take me another 8 minutes. I don't want to spare 8 minutes free. So that is the reason why I'm not going to run online. So yes, this particular application can be since we have just created an handwritten, recognizing handwritten digits single, and this can be extended to recognize handwritten digits as well as sudoku solver, something like I have written in my blog. You just place a sudoku to the webcam and you get the solved sudoku. You no need to mark the sudoku region, nothing. You will just get the solved sudoku one. Okay. So yes, the most and the challenging part in the building a deep learning model is the memory issues. So my machine have 2 GB GPU card. That means I cannot run out of that, at least if I'm going to run my model on GPU. And also it is going to take very much time. We have just finished classifying 10 classes here. So how about classifying the actual real world problems? Okay. So the challenge here is out of memory issues, and it will take many hours and sometimes days and sometimes many weeks of training. So I don't have that much of memory, and at least I don't have that much of time. Therefore I'm going to use a pre-trained model here. So the reason for we are using a pre-trained model here is the memory issues, actual memory issues. So here we are going to use a overfit pre-trained model, and we are going to use this model to train and classify 101 natural categories. I mean the general categories: cars, trucks, people, fishes, uh, birds, something like that. We are going to classify those classes. So yes. So since it is very hard to train a model of our own, as it will be taking lots of hours and great GPU memory, we can make use of a pre-trained model like Overfit here. Overfit is one of the model trained on ImageNet database, consisting of 1,000 different classes. Since we need to classify 101, 101 categories, also note that these 101 categories are not the same ones with which the ORFIT was trained on. ORFIT was trained on 1,000 different categories, and what we are actually going to train on and building the classifier on top of 101 categories are totally different. So we will use this pre-trained model to extract meaningful features from an image, and then we build a simple machine learning model on top of it to classify our Caltech 101. So the actual data set we are going to use here is Caltech 101. So okay, let me show you the data set. So, so this is the actual data set. These are the classes we have, and each class folder we will be having lots of images. So here I'm going to see the classes of mobiles. Okay, so some kind of cameras. So it has 101 categories, images, and we need to train our model in order to classify these particular. Okay. So just like the Facebook is doing. So I will show you. So Facebook Paytm has built this kind of application. I mean, not an application. The images automatically get tagged, and what if you wanted to see this, you just need to install and plug in either in Firefox or either in Google Chrome. It's up to you. It just describes whatever the alt content there under the image, and it just show you on the particular image. Here you can see one or more people standing in the outdoor. So this is the actual thing we are going to construct now. I mean, not exactly this much accurate. Okay, we are going to classify. Okay, this is a golf. Okay, this is a person, or this is a face. So this is the action we are going to classify. We are going to build to classify things. Okay, so we are going to use an overfit model. It has 6 convolution layer followed by 3 affine layers. You can see 6 convolution layer. Also it takes image a shape 231 of input shape is 231, as you can see, 231 height and 231 width. So whatever the image we are going to input, we need to reshape it to 231 to 231, so it would be fine. Okay, so actual overfit architecture is this. So the first convolution layer is 11 by 11, having a filter size of 11 by 11, and the stride 4 by 4. Pooling size is 2 by 2, and the pooling stride is 2 by 2. And again, input size is 231 by 231, as we have discussed earlier. So after going on through this, the input shape will become 24 by 24, which is greatly reducing actually. And then it passes on to the second convolution plus max pooling, and does 256 channels with 256 channels, and the filter size of 5 by 5 by, and to 96 again, the previous layer depth. Okay, and yes, we will be passing it, and we will be passing it through all over 6 convolution layer. I mean 5 convolution layers. I'm sorry, 5 convolution layers, and then we are going to take the output at this particular layer. So 3072, we will be having 3072 uh, output elements here. So if you are going to pass an image there, we are just stopping the image right at this particular layer and taking out the features there in order to build uh, our own model. Since the ORFIT was trained on different 1,000 categories, and we are going to classify between 101 different categories. These are completely different. That 1,000 and these are not different. So if you are going to use this particular overfit model to classify our 101 categories without training it more, then definitely it is going to fail. So that is not we are going to build. we are going to use this particular overfit trained model in order to build a classifier on top of it. So we pass an image and we just take out the feature vector from this particular sixth layer here. Okay. Okay. Now, and we will be using, I mean, since it just outputs 3072 nodes for each image, if you are going to pass in 10,000 images, it would be okay. What if you are going to pass lakhs and millions of images? It would be very difficult to store that. So one solution to that is using HDFI. HDFI. HDFI is a binary data format created by HDF group to store gigantic numerical data sets on disk, while facilitating easy access and computation on the rows in data sets. Data in HDFI is stored hierarchically, similar to how a file system stores the data. Data is first defined in groups, where each group is a container-like structure which can hold datasets and other groups too. So each group can hold datasets and the other groups too. Once a group has been defined, a dataset can be created within the group. A dataset can be thought as a multi-dimensional array or a homogeneous data type. Okay, so HDFI is initially written in C. However, we will be using the H5PY module. We will be getting into that later on. Using that, we can gain access to the underlying C API using the Python programming language. So what makes H5PY so awesome is that the ease of interaction with the data. We can store huge amounts of data in our HDFI dataset and manipulate the data using NumPy. That's it, nothing more than that. For example, we can use standard Python syntax to access and slice rows from multi-terabyte datasets stored on disk as if they were simple NumPy arrays loaded into the memory. So, yes, perhaps best of all, the HDFI dataset is standardized, meaning that these datasets stored in HDFI format are inherently portable and can be accessed by other developers using different programming languages such as C++, MATLAB, Java, whatever. Okay, so what exactly this does is just uh, if you are going to store huge data, it would be very difficult to fit into the memory, at least in the primary memory, so that we will be storing this on the disk and we will be accessing as if it was on the primary memory. That's it, nothing more than that. So yes, let's get into our overfit framework. So yes, so first thing we need to do is extract the features from an image. So Caltech 101, from each image we need to extract the features. Therefore, we need to we are here to create an extract features.py script. So we start off by importing the dependencies, and we are going to build an argument parser which just takes a single argument configuration file. The reason I'm using a configuration file, something like this here, is to facilitate, I mean, to be more portable. Here we are using Caltech 101. Maybe tomorrow we might be using some other different, we might be using different categories. So that is the reason why I'm not hard coding the actual pass. So we better use a configuration file like this. So here the datasets we are using is Caltech 101, which is in the datasets folder, you can see here. Okay, and then the features path, the actual output features, which are 3072 per image. So here if you are having 10,000 images, then the feature vector shape will be 10,000 by 3072, right? So that particular thing will be stored in the output Caltech 101 and features.hdfi. So what we have discussed earlier, HDFI. So layer number is -3, which does mean something like this. So here we are going to take the output from this particular last but 3 layer. So -1, -2, and this is the -3. This one, from this particular layer we are going to take the output from. So yes, from here we are going to take the output, and we need to reshape each image to 231 by 231, since the overfit expects the image to be of shape 231 and 231. So yes, the training batch size would be, I mean, not training, the extracting batch size should be 32. if you are going to pass in all the images at once, then definitely our memory is going to be exhausted. That is why we are going to pass 30 batches of size 32. Okay, so yes, label encoding. Since we have labels of not by numbers, we have accordion, airplanes, brain, Buddha, butterfly, camera. So these are the classes, and we need to encode them. Something like aeroplane is 1, Buddha is number 6, helicopter is number 7, something like that. Okay, and here comes our classifier path. The actual train model will be stored here, and using training size of 0.75. So 75% of the samples will be used for training, and the remaining 25 are used for testing. So okay, let's move on. So yes, we just take an we just build an argument parser which takes in a configuration file, nothing more than that, and we just loads our configuration file into the memory as a config variable. And yes, I'm going to find all the images in the particular data set. For that, I have been using list images function from imutils. If you don't know, if you don't have imutils, just install it by pip install imutils. That would be fine. Yes, the output size also, yes, we are expecting 3072, right? I have not hard coded that. I have not hard coded that. So if you are going to use this particular the seventh layer, which is last but 2, then you can simply replace -2 here, -3 by -2, then it would be fine. You will be getting 4096 features per image. Yes, 4096 features per image. So Spall network filter shapes is Escalante. Okay, one thing I forgot here is how actually we are going to use overfit is thing. Escalantiano module have already implemented overfit framework. Therefore, we can make use of that particular thing. So from Escalon-Theano.feature extraction, overfit transformer. So this is going to transform our image to whatever the layer we are going to define, up to whatever the layer we are going to define. So here we are defining up to the last but 3 layer. So yes, that would be fine. Yes, we are getting the batch size. Yes, since we have discussed about HDFI, as we have discussed about the HDFI. In HDFI, we will be creating groups, and the datasets will be created in that groups, so that we are creating a HDFI file here by using h5py module, which I have imported here. Okay, and then I'm going to create two data sets in order to save image IDs, which are the names of the images, and the features, the actual extracted features. Also note that the actual shape is length of image paths. I mean the number of images we have. We can also make it dynamic, something like none by so and so. Also we can make it as maximum shape. So to make it very simple, I didn't make it like here. Okay, so here the data type is special data type and Unicode. Since these particular labels are text, we are going to use Unicode for that. It would be better fit for that. And for the features, we are using the float data type, which is good. Okay, I just added a random seed of 42 in order to reproduce the results, nothing more than that. And yes, I just import. Therefore we can encode labels, something like initializing the network, I mean transformer. This script actually downloads 1 GB of actually pre-trained weights from Escalon Theano, some website. I don't know, maybe they have been uploaded it to some Dropbox, I don't know. Okay, so output layers, we need to define at which layer we need, up to which layer we need to transform the input to, which is defined in config.json, I mean the our configuration file, which is -3 up to the last but 3 layer we need to transform our input to. Yes, we are going to extract the inputs. So yes, we are just creating a batches, so that's nothing more than that. We just read the images as a list. We have just a list of batch 32, so this list will be containing 32 images, raw images. And then I'm going to resize each image to whatever the image size I have defined here. 231 by 231, because since this particular overfit framework expects the image size to be 231 by 231, so I'm doing that. So image id db is something what I have created here for storing the image ids, and features db for features, storing the features. Okay. Yes, we can simply